Hello everyone. In this fourth tutorial of the series on fire and smoke with a fluid simulator in Blender 4.5, we'll take a detailed look at the parameters of the three types of flow objects used in the physical simulation of fire and smoke. As mentioned in the introductory video of this series, the PDF version of this and other episodes is available for free download at the link you'll find in the description. In the scene I'm using, there are some logs placed inside a fireplace. These logs form a single mesh object, which will set up as an inflow. I've already created a domain for the simulation, enclosing only the volume of the fireplace. I assign a fluid component of type inflow to the logs. The fire and smoke mode includes both the smoke and fire parameters, so I choose this combination in order to analyze all of them. Later, I'll point out which parameters belong only to smoke and are therefore not available in fire-only simulations. As you can see, there aren't too many parameters. By default, the flow behavior is set to geometry. As we know from previous episodes, this mode produces an initial burst of flame and smoke, after which the object will no longer emit either fire or smoke. It can be useful for explosions or single puffs of smoke, but in our case, we need the inflow mode. In any case, aside from the use flow checkbox, geometry and inflow share the same parameters, so we'll examine all of them by looking at inflow. From the previous episode, you already know that to control the amount of flames produced, we can adjust the fuel parameter. In our case, we can lower it a bit to generate lively but not excessive flames, or lower it a lot to create glowing embers. I reduce the size of the domain a bit and increase the resolution. Before examining the inflow parameters, let's see how to make the smoke inside the fireplace disappear using an outflow object. Outflow objects are meshes that make fluid simulation elements, whether fire or smoke, disappear upon collision. I'm adding a simple plane to use as an outflow, placing it at the top of the fireplace where the smoke would normally rise into the chimney. Outflow objects, like inflow objects, don't necessarily need to be visible in rendering. So I'm disabling the visibility of the outflow object both in the 3D viewport preview and in the final render. From now on, I'll select it in the outliner. I then add a fluid component to the object, set its type to smoke flow, and its behavior to outflow. This type of object has very few parameters, and in fact these are also present in geometry and inflow object, so let me briefly describe them. This planar option should be selected if the object has no volume, or more generally, if it isn't closed. Since the plane is exactly this kind of object, I enable this option. The use flow parameter allows you to enable or disable the inflow or outflow, and it can be animated, making it useful if you want to create intermittent or non-continuous emission or removal of fire and smoke in an animation. The sampling substeps parameter defines the number of additional simulation steps calculated between frames, improving the quality of the simulation. It's very useful for fast simulations, and even a low value, such as 3, produces noticeable differences. Surface emission and volume emission provide offsets for the emission or capture point of fire and smoke relative to the object's surface or volume, but in this situation we don't need them. We'll talk about flow source later. Playing the simulation, we notice that at first everything looks fine, but at some point a bit of smoke manages to escape upward. Increasing the number of substeps doesn't change the situation. Making the plane visible again in the 3D view and changing the viewpoint, the solution becomes clear. The plane is too small, so at a certain point some smoke escapes outside and rises. The only solution is to resize the plane properly and try again. Okay, now let's examine the parameters of the inflow object in detail, except for those we already covered with outflow. Smoke color actually refers to the color of the smoke in the 3D viewport preview, because the rendering color of the smoke is defined elsewhere. Assigning a different color here can be useful to identify smoke more easily in complex scenes, or to use this object attribute in shading to change colors or other aspects of the domain material. The absolute density field is enabled by default, and generally it's better to leave it that way, because it ensures there is only a certain maximum density of fire and smoke within the domain. If disabled, fire and smoke can increase dramatically, sometimes resulting in a kind of uncontrolled blaze. Here, the effect is limited by the presence of the outflow, so I'll temporarily remove this object from the domain to show you how the flames increase. Disabling absolute density can be useful in some scenarios, but in most cases it isn't, so I'm turning it back on. The initial temperature and density parameters refer to smoke, so they're not available in fire-only simulations. Density refers to the amount of smoke to emit, and higher values correspond to larger volumes. In fact, for the scene I'm using, too much smoke is being emitted, so I'm lowering this value. The initial temperature parameter defines the difference between the temperature of the smoke and that of the surrounding environment, and it controls how fast the gases rise. Its effect, however, is tied to a domain parameter called buoyancy heat, so we'll examine it more thoroughly in another episode. So far, I've made the inflow objects emit flames across their entire surface, but it's possible to limit the emission to only certain parts of the objects by selecting vertices in a vertex group and then specifying the name of this vertex group in the flow component's dedicated field. Another tool that lets us add variability to flame emission is texture, found at the bottom of the inflow panel. Here we can assign a texture and, most importantly, an offset field, which defines which slice of a procedural texture to use. Procedural textures, such as clouds or noise, are not two-dimensional images but actual three-dimensional volumes. By animating the offset value along the timeline, as I'm showing on screen, we shift the texture vertically using a different pattern each time for the emission. This gives the flames a less uniform look. The issue with this system is that it usually requires multiple attempts to find the right combination of texture type and offset change before achieving a good result. The tools in the initial velocity group allow you to give flames an initial direction and speed. Their fields have fairly intuitive names, so there's not much more to say, but I'll still show a practical example with another scene in a later episode. Finally, we have the flow source field, which lets us choose between mesh and particles. The meaning is straightforward. So far, we've used mesh to emit fire and smoke from objects, possibly limiting the emission surfaces with vertex groups. But objects can also have particle systems, and sometimes we may want those particles, rather than the emitter, to produce fire and smoke. In that case, we need to select particles as the flow source and, of course, specify which particle system of the mesh will drive the simulation. As you can guess, we can assign a flow component either to the geometry or to one particle system of the selected object. That's it for this tutorial. We've seen how to adjust the smoke effect a bit with textures, but the flames are still too uniform. To add turbulence, we need to tweak the domain parameters or use force fields, but we'll talk about that in the upcoming episodes. If you enjoy my content, the best way to thank me is to subscribe to the channel and leave a like on the video. Thanks, and see you soon.